Uh, so good morning, good afternoon, good evening, everyone. We are now in the second talk of our online forum, and today our speaker is Simon Deleonibus. He is a past chief scientist of Université Grenoble Alpes. I hope I haven't messed too much with the pronunciation. He also is a life fellow of IEEE, an emeritus fellow of Electrochemical Society, and CEA research director. Now, with this brief introduction, I would now like Simon to start his talk with a brief introduction of himself first. Simon, now over to you.
Okay, thank you very much for your nice invitation to this very interesting and exciting forum on climate change technologies. I'm Simon Deleonibus. I started my career after a PhD on photovoltaics in the microelectronics business. So I was very interested by semiconductor technology and components. And then I joined the industry to develop and transfer to production advanced technologies and products. Well, I invented some very useful and widely used technology for the industry, which is called the plug technology, which is a generic patent for interconnect, so that everybody is using today in the microelectronics industry. Then I joined LETI 5 years later. LETI was part of the Energy Commission, and I stayed there. Well, I started as a development and research engineer, and I stayed there until my retirement as chief scientist in 2016. So, okay, you can look at the details in my biography, which might be on the website of the forum. So my talk is about the device engineering. So I've been working on device engineering through all my career, so more than almost 50 years now. And the main concern about microelectronics and all electronic components has been about energy and variability efficiency, besides getting the proper performance. And well, right now, with the rapid development of artificial intelligence, for sure, we are in a energy and variability efficient era, which we must take care of. And sustainability is really something we should look into. Well, especially that we are now concerned by a huge number of components on a chip, and also because our systems are more and more scalable from the nanoscale, from the nanometer sizes up to huge systems like computers. So I will give some details. So here you can see the progress. Oh boy. Sorry, there's a problem. Oh boy. Okay. Can you see the slide?
Yes, I can see the slide. Yes, Simon.
Yeah.
I think I have a problem with something, some audio. Oh boy. Okay. I need to take this out. I don't know. Okay. Sorry about this. Okay. Is it okay now? Yeah. Okay. Well, scaling in microelectronics has been I would say a success story. Since the invention of integrated circuit in the late 50s, 1958 namely, well, we had one active device per chip, basically, and also other passive components. Until now, we are dealing with, well, it goes out of this scale, the scale of this graph, but we are dealing with hundreds of billions or thousands of billions of devices on a chip. So this is really an unprecedented progress in all human history about in technologies. It's been a succession of things that were impossible to make. So the progress law of microelectronics is called Moore's law. So basically, you increase the number of devices by 2 every year. And then what you should know, and what people have been struggling with, is the fact that an incubation time is needed just to put these technologies on the market. So why? Because you need to scale down the, let's say, the lithography capabilities. So you can see that we've been going pursuing a nanometer down to nanometer scale wavelength scaling, and we need it at the same time. And people forget this. Most of the time, they forget that we needed new process modules. You can see in black here. So polygate, after the metal gate, there was polygate, polyside, etc., etc. We needed to introduce almost at each generation, and now we're dealing with 3D and also other type of approaches to enrich the capabilities of our integrated circuits. So it's very important to keep that in mind. Here in yellow tab, you can see the main applications that have been possible thanks to this approach. Well, I said that the energy and variability efficiency are main concerns. Sorry. We've been reaching a number of exchanges in information down up to 10 to the 24. So it's a yottabyte level. So there's an ecological footprint for these for AI for integrated circuits. It consumes more than 4% of world electricity, and right now it has an impact on CO2 emissions, water resources, and well, this is mainly due to AI growth issue. There will be a scarcity of spice metal and rare metals that will come around the corner, and we need to keep in mind that the market drivers are autonomous, nomadic, heterogeneous, and AI is rapidly coming around. So we need a ultra low power, high performance, and drastic variability reduction. So here you can see that the electricity consumption that will be needed in the next years. So this is according to the SHIFT project. Due to the increase of the needs of AI and also cryptocurrencies. So you can see the part of consumption without AI here, okay, in this color, this light blue, and the currencies, cryptocurrencies needs. And AI here is rapidly growing, and there has been a sort of shift after a trend break in 2023, especially with the new applications, AI applications like ChatGPT, namely, that has been coming up. There will be a conflict sharing resources with our other electricity consuming sectors. So the problem is, will energy production meet plus 200% needs? This is what the graph shows. And this will, for sure, degrade the world CO2 emissions, especially in USA, due to recent political decisions, 9% increase instead of expected 5% decrease. So there's a paradox, moreover, raised by the SHIFT project. No international AI roadmap for applications having international impact have been proposed. So this is very important because we have seen that the progress of microelectronics has been possible thanks also to the fact that there was a international roadmap of technology. Okay, now I will explain how this has been possible. Okay. Okay, so actually people talk about more and more, right? And we'll see that thin film devices, thin film channels are very important to that respect in order to manage low power and high performance. And also we'll see that we will need something like zero intrinsic variability in the future, because we're really incredibly highly increasing the number of components on a chip or on a nanosystem. So here you can see the structure of a MOSFET. Well, that's the basic component in all our circuits today. So made of metal, source and drain, and a channel that allows electrons or holes to flow. So the basic rules for scaling, besides reducing the gate length, needs to scale also the source and drain depth. So one of the ideas that was brought up was to use thin SOI in order to confine the charge in a thin film and avoid any bulk leakage that has been identified as a limitation to scaling. So furthermore, if we want to achieve ultimate scaling, so we need to reduce this channel thickness, and to obey that has to be some rule that you can see here. And as you scale down and add an increasing number of gates, then you can end up with something which looks like a nanowire or a nanobeam with an infinite number of gates. So just that's what people call a gate-all-around structure. So you can see here some TM micrographs that we have been using in our publications since, you can see, as early as 2006, we proposed all these architectures that I've shown you by using thin films. You can see, for example, fully depleted SOI as thin as 2.5 nanometer. So here you have a tri-gate. Here you have a double gate with very aggressive gate length. Then nano beams and nanowire that we have shown as early as 2006 and published in 2008. So well before Intel, just to mention it. So this scaling optimization goes into the sense of increasing the electrostatic integrity. So basically, it clamps the leakage current and the two-dimensional effect. And also, this rule relaxes the scaling rule by the architecture. So right now, many people are using FinFET. It's the same approach, or Tri-Gate. It's the same approach as the one I've described. So here, you can see some results, for example, on fully depleted SOI devices designed in the 14 nanometer node. So this is the design of SRAM. You can see on this TM micrograph, and two transistors among those, N channel and P channel, and these transistors have a silicon thickness as where the channel flows, where the current flows in the channel, as thin as 6 nanometer, and a buried oxide thickness of 20 nanometers. So these devices are completely isolated. So here you can see some statistics made on the film thickness after fabrication, and of course, there's some film consumption during the process, and you can see that the range of max to min thickness is quite manageable. These technologies have been shown to have a record high VT matching performance. I just invite you to look at all these publications I mentioned in the bottom here. And well, this is a matching parameter, Pelgrom parameter. Low power and high performance are possible to manage on the same chip. So it outperforms the bulk technology by the leakage, lowest leakage, the best delay and power delay product. So design platforms have been proposed by the industry and in collaboration with us. So here I mentioned ST, IBM, and but there are other companies like Samsung and Global Foundries, and also in Japan, Toshiba. They have been proposing such platforms, and the scalability has been proven down to 8 nanometer gate length. Not I'm talking about the gate length, not the node, the technology node, which is something else. Okay. Oh, boy, I forgot this one. Oh boy. Okay. Okay, so here you can see that at low supply voltages, or at high at high supply voltages, you can see that we have tested this technology to extremely low supply voltages. Thanks to the drastically reduced varieties capacitance due to isolation of these films, you can reach much higher performance. So it's very important to keep this in mind, to reduce power consumption, because it very drastically very strongly depends on the supply voltage. So basically, for a given I don't know where this bug came from. I'm sorry. Oh boy. Okay. Okay, so I talked about the ultimate scaling into nanowires. So here you can see how we, I would say, elegantly made these nanowires as early as 2006. So very recent publications by other authors at IDM, other companies have shown this approach. And you can see that we were among the pioneers. And so you here basically how do you do this? You just grow a superlattice of silicon, germanium, silicon, and alternatively, well, you what you could do is superimpose up to 20, if you wish, up to 20 of these layers of um, these epitaxially grown strain layers, semiconductors. So you remove silicon germanium very selectively to silicon, and you leave silicon. We have we developed a etching process which had very high, more than 200 selectivity. So you can see that then you can deposit the dielectric, here hafnium and also metal gate, here tinitride on this example. And you can see, so you have stacked nanowires. And then you can play with the process and introduce some isolation in between the wires. And this allows you to reduce the parasitic capacitance because you have a very high, much higher parasitic capacitance here, gate capacitance on the nanowire FET on A example compared to the B example. And you can also just etch and leave silicon germanium, and you can just make a FinFET or and separate two gates. So you can play with the process. Of course, you need to introduce new steps, and that complicates and increases the cost. Okay, so you can make nano beams as well, as you can see here. This is one of the first realizations at that time. And what this process brings you is the fact that you can get low power and high performance, so extremely low leakage current. So this is a 50 nanometer device. You can see that extremely low leakage currents, or you can also take advantage of the architecture to get very high output currents. Okay, so I talked about the fact that sometime scaling all these layers or devices or features to very thin features, we would need some zero intrinsic variability approach. I just listed a few topics to address, very important to me, I think, and well, to many people. Dopant control at the single atomic level is extremely important because the number of ions you introduce in the channel is reduced drastically, and you can, for example, for a 20 nanometer device, you can get at the most 10 dopants if you have a concentration of more than 510 to the 18, which is quite high. So this is very important to limit some random doping effect. So there's a certain number of techniques that have been tried, still I tried today to reduce this problem. Anyway, the intrinsic channel is a very important option. However, you could have some single ion migrating into the channel. I will show an example. Monodisperse patterning also is very important. Self-assembly block copolymer have had in lithography some success, and self-limiting drying, self-limiting chemical dry etching as well. Interconnect with monodispersed features and object. Well, I don't think there's a standard solution today, but people have tried CNT, MIM contacts, DNA templates. Well, it's a putting that into introducing that into a process is quite difficult. You need aqueous media for DNA, for example, and CNT grow by bundle. So it's very difficult to manage only one carbon nanotube or two or unit by unit. So MIM contacts are some, let's say, more semiconductor type of approach, but well, still people are working on it. Few to single electronics, that makes sense when you reach that level of very fine features as less than 10 nanometer. That's becoming a hurdle. This is why the gate lengths in all the circuits you can see today, instead of even in what is called 1 or 2 nanometer node, technology node, are not less than 12 nanometer, 10 to 12 nanometers. So people are struggling to use even smaller devices. That's an issue. Well, we have shown that with fully depleted SOI, it's possible to have down to 8 nanometer devices before you go to gate-all-around structures. So for memories and logic, there are some opportunities, especially in quantum computing by spin manipulation. I will show you an example. And the other question that comes up is, are atomically thin active 2D semiconductors challenge silicon? So people have been looking into many material. Zero intrinsic variability is a real question. Material physical properties of atomically thin sheets need to be really mastered. Opportunities to silicon add-ons and diversifications have been proposed by using this, well, it's sort of a serendipity type of event that has shown that you can use these films for other applications just that do not compete with CMOS. So here I'm just showing on the right hand side the DNA molecule, which is not more than 2 nanometer in feature. So we are in that scale. So here you can see what you can achieve by exploiting single electron phenomena. So here on the top left, you have a transistor. So the source and the drain, you can see the arsenic atoms. This is an N-channel device. Well, the channel of this transistor was supposed not to have any dopant. Actually, some dopant migrate stochastically into the channel. And you can see at very low temperatures, you can see diagrams like this, which is what we call a Coulomb blockade type of diagram. It shows that single electron phenomena are occurring. The white area here, well, this is the drain voltage versus gate voltage. So this is in this white area in the middle, you can see that no electron is allowed to enter into the channel. So you can block the passage of the electron. And in other cases from, let's say, ranging from dark red to black, you can see that there are some forbidden or allowable situation in between. So this is the discrete nature of dopant is really well, it is really shown. So by playing on the structure of the transistors, you can you can make artificial atoms just by controlling the well, the potential well under a gate. So here you can trap in these conditions, you can trap one electron, or allow not allow another electron to enter. So by playing on the let's say the allowable number of electrons, if you have an electron of the same spin on an adjacent transistor, you can see that, well, you're going to trap an electron and have an electron with a given spin. Okay, in this other case, you can allow the passage of the electrons on the other side, because only two electrons can stay on the same level. So this is a basic quantum mechanics. And you can see on this graph that you can define domains here in gray, where you can allow or block electrons, block the passage of electrons, and let's say by just playing on the spin of these electrons by using a given gate electromagnetic, applying an electromagnetic field on the gates. Okay, I'm not entering into details. I can leave this for the discussion later. So we're talking about something which looks like a polyblockade spin manipulation. So this needs a very low temperature to get a very clean, very clean features on the graphs. So people have been using this for many applications. Well, electron pump, multi-valued logic. And now what has really been emphasized lately, so we've been working on this for, let's say, 27 years already, 26 years, well, almost 27. Highly scalable quantum computing is possible due to this spin blockade effect. So CLAT, so, and CNRS, I've been starting, so just when I was leaving for retirement, people from my team started this company called Quobly, and to build a silicon-based quantum computer. So I just show you very briefly here on this graph. Well, this is a very nice graph showing you how the number of issues you have to address, number of topics you have to address to build a computer. So they are using this spin blockade technology to, well, just build a quantum computer. So they started to make test benches to develop modules for module developers and end users for quantum computing, including software and chip design. They work with IDMs, with some medical research institutions or companies, drug discovery, mobility, energy engineering. So there's a wide number of topics that have to be addressed, and their approach is to to address some specific and build some specific system for end users. So they will reach 1 million, more than 1 million qubits by 2030. So this means that you would manipulate instead of two levels, you would two bits, sorry, per device, you would be able to handle 2 to the 10 million qubits. Okay, so here I mentioned the 2D crystals regarding the scaling of transistors. So here you can see on the left-hand side that scaling the film thickness, or what we would call a quantization length, increases the band gap of from if you evolve from 3D semiconductors to 2D or 1D semiconductors. So, well, it's a dramatic situation for 3.5s, and for silicon, it's a little bit better. However, reaching very small dimensions, that really poses a problem. 2D crystals make sense. So let's say, namely, 1 atomic sheet as a thickness, and it's not very easy to deal with these materials because basically their properties, their transport properties, so you can see the mobility as a function of impurity density in these films, their properties will depend on the interfaces, above or bottom interface. So you can see that the mobility here, low field mobility, varies really drastically. So it's extremely difficult to handle these kind of technologies. Moreover, you can see on this example, this is for MOS2, the same as on the left-hand side. You can see that whether you have one monolayer here or 2 monolayers stacked on each other, you have different materials, direct band gap or indirect band gap. So 0 intrinsic variability is necessary because you cannot allow to have 1 and a fraction of monolayer and with a dispersion on a chip, for example, which wouldn't allow you to manage the number of carriers in a channel, basically the current output current. So this is really an issue with this kind of materials. You need a 0 intrinsic variability approach. So here you can see a list, given here for all the materials that have been tried or have been we've seen publications on. These films are flexible due to their thin, to the very thin, to the thickness. Sorry, they're transparent, also for the same reason, highly conductive. So the mobility is quite high. So here you can see some nice applications that I would say as an add-on application to a silicon chip that you could use. So that has been shown already quite a few years ago. And basically, if it's an indirect band gap with MOS2 has an indirect band gap with one monolayer, okay? So this means that you can emit light in a heterojunction, which is shown here, MOS2 on p-type silicon. And on this insulator, you can also design a circuit with a source just to actuate this this heterojunction and emit light. So whatever, you can use these for many applications like displays, for example. All right, now the sorry, I think I mixed up with my version, different versions of okay, here. Okay, now let's talk about the system integration evolution. So we talk about more than more diversification, and we are going to see that 2D to 3D co-integration of more and more than more devices will be necessary. So, well, when we talk about systems, we need to think about how we manage memory. So the memory hierarchy has been quite consistently revised in the past 20 years, 20 to 25 years. And basically, for high density memory, we need a standalone just to interface a circuit with the outside world, I would say. So here you can see the example of it for a non-volatile memory. It could be a DRAM, by the way. Then you have another approach, which is more more dependent on the architecture, and especially if you want to personalize for a given application. So this is, you need some memory inside the circuit, so it's embedded either with a high density, or it can be distributed with very aggressive feature size. So we can exploit the granularity of the what we need, and in terms of application. And you can see that so here you can use this, for example, to reduce power consumption, or even implement new architectures like associating logic and NVM for many purposes, power reduction, or also neuromorphic needs type of architectures, in-memory computing, and also, well, now what's coming up is also machine learning for AI, or, sorry, I did not mention, but for robotics also as well. So I mentioned the fact that 3D is a major option to increase increase the number of devices on a chip, because scaling of transistors has become quite problematic for the reasons I've explained before. So the highest density you can get for 3D would come from the possibility to stack devices one on top of each other, where active devices, these I would say transistors, for example, N-channel and P-channel. And this is an example of one of the publications that listed here. So this is basically two transistors with different gate lengths. So you can mix several generations, several nodes. You can also facilitate the, let's say, in-memory computing by just implementing memory on top of logic, or you can also integrate high-density sensors or actuators on top of CMOS devices, type of devices. So here you can see three examples that I invite you to look in the literature. Are in all these publications. We have been working on that since 2006. And well, actually, what you need here to develop this technology is really cold end processing. So here, this is an example of bonding silicon on top of already printed circuit, low thermal budget, and this offers you also the possibility to stack on top of a silicon chip other semiconductors with their specificity. So I will not enter into details here, but this is open to new type of technologies and applications. There's obviously a layout improvement by partitioning. So you can say one node per stack layer. So you can stack several layers up to, it has been demonstrated that up to 3 layers, there is no issue about the performance or main figures of merit. And this approach increases the density of vias by 100 compared to a packaging approach I will show later. You have an interconnect delay reduction. Of course, the distance in between devices is very short. And so you can drastically increase the speed either for low power or high performance applications at very low supply voltages, or at for a given static power dissipation. So this opens the way to high density embedded intelligence. So you can mix all type of devices you wish. Of course, this is going to increase the cost, but it offers a good opportunity to develop new applications, and with volume, the cost could be lowered in the future. So now, okay. 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 The packaging approach I mentioned is given here, and a little bit different than a conventional approach. And this system on wafer approach, you can see that if you use what we call, instead of sequential, you use parallel 3D, then you can reach the point where you could get zero power from a grid system. This means that, well, basically what you would need is to process high density interconnect on wafers, high density interconnect on chips. Well, on wafer, in a wafer fab, and then stack circuits on top of these, well, at the wafer level. You can stack circuits or even other type of devices or sensors, and then what you can do is then assemble everything. So you can need well, new well, other process modules. I would say those, well, they're not new, but I mean different from what I've mentioned at the very beginning. This is more a packaging level type of technology by using some base wafer coming out of the fab with nice interconnected features. So it could be optical interconnect, and also you could cool down with some other technology. the whole system. Here you have a system, a complete system that if you add some energy harvester, uh, you can make this completely autonomous and get no power from a grid or least power. So this could be a good way also to reduce um, uh, the power or energy needs in this business. So all other features you would need um, antennas just to communicate, and also, well, of course, you would need some wafer level packaging approach to deal with. Okay, so the future is just what is explained here on this graph, mixing, let's say, a more approach with more than more approach by by stacking several, well, different type of circuits or features or devices. And well, these are some, let's say, some application that have been mentioned to use this type of integration. So it's a new playground that could be extended to so many sectors, and many of these could be should be power.
Simon,
Okay.
sorry to interrupt. We have 5 minutes, and then we will take a few questions.
Okay.
So we can
Okay,
wrap
I'm
up.
coming to the conclusion. Okay.
Okay.
Yeah. So okay, I'm sorry. Been a bit long due to this issue here. I'm sorry about this. Okay. Energy harvesting. Well, many techniques have been mentioned. Well, basically, energy harvesting is okay if you're getting it from unwasted energy and not uh, some any system that has a high power consumption and produce a lot of heat, and then you try to use this heat to uh, uh, transform it into electricity. So here you can see the possibilities you have in terms of energy harvesting depending on the technique. Um, so photovoltaics, of course, is among the most interesting one whenever you can use it, outdoor or indoor. Micro batteries are very important in that area to implement on a system. So here you can see that for bio applications, for example, you need some flexible, foldable, stretchable devices. Okay, this is my conclusion. Silicon CMOS will be the base platform beyond the roadmaps, hosting novel process modules and add-ons for diversification. I've shown you that there are alternative computing possibilities of high density quantum computing. That's the fact that you can use silicon transistors uh, gives you the possibility to scale it, to scale quantum computers, neuromorphic at very low cost, neuromorphic architectures, diabatic, I did not mention, but this is also possible, very low power. Heterogeneous 3D co-integration, whether it's sequential or parallel, will allow you to manage low power and high performance, add-ons, and also some devices that are autonomous and do not need power from the grid. Sustainable development has to go towards cramming more integrated sustainable function on a chip. So I'm just mimicking one of Gordon Moore's phrases about cramming more devices on a chip. Okay, thank you.
Thank you very much, Simon. It was really a nice talk on this energy efficient devices. So we have a few questions. So one question that I received in the chat box is, can AI centers pay a tax or higher cost per kilowatt hour for such a situation? Because you mentioned that AI is energy consuming.
So let me rephrase that. Is that the question is about the power consumption of AI?
Yeah. And the question is whether those who are using AI, can they pay extra charges for this? Is
Or if
there
they can
a
pay, why not?
so how will these be implemented? I mean, how do you know that some processes because of AI in the device level? Is there anything to figure that out?
You need to reduce as much as possible the power consumption of your devices. And then, as I shown you, 3D is something we should really go into and teach our students to use, just like I would say new type of libraries. We need to really make this popular. It's sometimes um, some technology has a high cost at the very beginning, but with some killer application, then well, if you get a volume, then you can reduce. It's a sort of a chicken and egg issue, right? Right. So you can reduce the cost, and I've shown you that 3D is a nice approach to reduce power consumption, to let's say to reduce the delay at the same time. So for many obvious reasons. And
Mm.
okay, so it's really sometimes you really need to look in you need to continue to develop technology and also science, uh, find new solutions with materials, with uh, also I would not forget the software as well. So it's our system approaches. Well, you need to really be conscious of many, let's say, make many put many types of skills together. It's very important. So uh, I don't know if I answered to the question, but
Okay, I see. So I
it's
can
not it's
see
not
another
it's not a binary problem.
I understand. So there are a lot of complexity associated with that. Okay, so I can see another question, which is by Professor Dahiya. He is here. So he asked that you mentioned somewhere that IC is requiring 4% of total energy, but this is during the use phase. There is a lot more needed during the manufacturing phase. So how could we reduce the usage of energy during manufacturing phase? When you manufacturing IC, that also requires a lot of power. So is there anything that we can consider about that?
Oh yes. For a time, for some time, there was sort of let's say strong debate about EUV, right? I suppose that's what you're mentioning. Is that what you think of? The power consumption of extreme UV steppers?
Yeah, that's correct. Yes.
Yeah, that's the hardest part. Um, and there was many people have been working. I mentioned a few techniques people were working on. Um, by the way, uh, some STM approaches for lithography were mentioned. Um, Also, the use of block polymers, which would not need very small wavelengths to reach a given. You see that there's no, it's not, you don't have the same rule to reach a wavelength as for standard lithography. So you can reach um, much more aggressive feature size without needing the lithography at the good level, at a classical lithography. So for many years, EUV did not show up, and probably the future is to reactivate these. I'm sure now that some people are still working on these topics, reactivate these topics about, let's say, some type of low-cost lithography. I mentioned STM, for example, which can help you to draw very small feature size. Well, just by using STM probes. So arrays of probes. So there have been several, many articles reporting results on that. So right now, the fact that extreme UV has come up, well, people are using it. However, as you mentioned, power consumption is a concern. So maybe the future will be a mix. Who knows? This is my my answer. I don't see now, unless we see new sources of EUV generation, we should go into mixing several technologies for lithography.
Yes. Okay. Okay. I can see that our next speaker and next session chair both are here, so we are running out of time. But I have one last question to you, which is related to the material. So the devices that you have shown is mostly silicon devices, but nowadays people started doing research on 2D material-based FETs or devices like MOS2 or graphene. So do you think these devices have a future as far as the energy efficiency is concerned? Do you think that these devices can be used for the purposes that we use in silicon?
Okay. What we need there is a very professional and serious roadmap, because, well, introducing a new material, as I mentioned at the very beginning of my talk, requests some time. So we have at least 15 years incubation time. So when I say this, well, all the people participating to the ITRS were conscious about this, that we needed some incubation time to introduce some new solution. And especially on the material side, this is a huge, huge, huge challenge. You need, at the same time, you need what in French, there's an expression saying, we need the butter and the money from the butter. So this means that you need 300 millimeter wafers, depositing these materials on 300 millimeter wafers with a defect density which is comparable to what you get on a standard 300 millimeter silicon wafer. So, and probably in the future, it will be 450 millimeters. Well, it's coming up soon. So we need a serious roadmap. I haven't seen a serious roadmap regarding MOS2. And okay, people can publish some articles and some papers. I've shown you some nice application, but because these materials have when you're using one monolayer, they have some nice optical properties. Okay, so light emitting properties. So you can use these tricks, these properties to implement other functions, not necessarily competing with silicon transistors. And moreover, I can't remember the dielectric constant of MOS2. I suspect that the parasitic capacitance will be much higher than in silicon. So I'm a bit skeptical today to see those materials competing straightforwardly with silicon. The future will be a mix. I mentioned the fact that with a 3D approach, a sequential 3D or other type of 3D approaches, you can mix all kind of technologies now. Because we have very good clean rooms. We should keep this in mind.
Okay. Thank you, Simon. So as we are running out of time, I would like to thank Simon again. And I would like to hand over this virtual platform to Dayalan to introduce our next speaker. So Dayalan,
thank you very much. And I would just invite you to look into these books that I've been directing a collection with Penn Stanford and Jenny Stanford, and also this invited paper at in the Journal of Electron Device Society quite a few years ago, but still things are are actual, I would say. Okay, thank you very much.